Hi guys, this is Minar Elaassar, as known as Dr. Minar Elaassar this semester. I hope you're all good and safe and most importantly ready to decide for one of your most important milestones in your career, your bachelor project. Today's video or presentation is intended to give you an idea about the bachelor projects I'm offering for spring 2022. Now, it is known that the Internet of Things IoT applications are rapidly and densely growing, where 75 billion devices are expected to be connected by 2025. That's more than the number of people on Earth. And an IoT application can be anything, like connecting an entire smart city or even your alarm clock communicating with your coffee machine to prepare your favorite latte in the morning. So everything will be connected and the applications are endless. Accordingly, the market and research community is challenged to provide a connectivity solution or technology that must be easy to use and install. We need a network to support this massive increase in the number of connected devices. And among the communication technologies that we know to provide the needed connectivity for IoT, like Wi-Fi and Bluetooth and cellular network, long-range, low-power, wide-area network stands out. Why? Because the technology provides long communication range where data can be sent over long distances, reduced transmission rate where data sent is of small size and sent infrequently, and it preserves the battery lifetime over many years, thus making it ultra low power. And these attributes typically describe an IoT application, and thus LoRa LPWAN is a perfect fit for the need of IoT. So let's go technical to see why LoRa LPWAN is a popular technology used worldwide. This is basically attributed to two major components. First, the LoRa representing the physical layer which uses the chirp spectrum modulation. It uniquely relies on 6 different programmable spreading factor ranging from 7 to 12 and low receiver sensitivity that they can achieve. The transmission bitrate is governed by this equation provided by the LoRa specification, which is a function of spreading factor, coding rate, and bandwidth used. So the LoRa physical layer leaves the network topology organized into concentric circles of multiple coverage spreading factor ranges, where each spreading factor represents a parallel network. So from a top view here, you can see that nodes allocated spreading factor 7 will exist around the gateway up till their service radius. And the service radius is the radius ensuring correct signal demodulation using spreading factor 7 in this case. And nodes with spreading factor 11, for example, can be found anywhere from the gateway up to their service radius here, spreading factor 11. So it is clearly explained that the higher the spreading factor a node uses, the longer the communication range it can achieve. But it is also clear from this equation that the higher the spreading factor, this means lower transmission bit rate. And consequently, this means longer transmission time. And a longer transmission time means more consumed battery power. So it is basically a trade-off. The second component is LoRaWAN network architecture, which is a simple star topology. It's composed of minimum number of elements. We have the end nodes, the gateway, and connected to a network server that connects to different application servers. Now, the end nodes, which are IoT sensors or actuators, they take advantage of the long-range communication that we just described of LoRa, and so they transmit their sense data over a single hop, and this single hop is even using an ISM frequency band, which means there is no cost, no added cost here. Then the gateway forwards or relays the messages between all end devices and a central network server. The gateways are connected to the network server via a standard IP connection, and it acts as a transparent bridge, simply converting RF packets to IP and IP to RF. Then the the network server function is to connect with the different applications. So this is a very simple design architecture, making the network easily managed at a very low cost. And at this point, we have highlighted all the key characteristics of LoRa LP1. Now, one bachelor project can be easily described here, which is simulation and evaluation of the LoRa multiple gateways. The idea is that we want to inspect the deployment of multiple gateways within the same vicinity. It may have an effect on the probability of correct packets delivery. So let's take, for example, this node. If it's using the previously installed gateway, so it's going to use a spreading factor 12, as you can see. And if it's using the new gateway to transmit its sense data, it will be using a spreading factor 11. And so it stands a better chance to transmit because it's closer to the gateway. And at the end of the day, both gateways are connected to the same network server. So packets lost or collided at one gateway may be still received by another one. Does this increase the overall network performance? The aim of the project is to try to see how many gateways should I keep on providing to increase the overall network performance. Also, at what position should I be placing these gateways? Should I go further or near the first or second or third gateway? Okay, so the aim of the project is to develop a simulation model for multiple gateways by extending the currently built single LoRaWAN simulation model or LoRaSIN and testing and checking upon the trade-offs that's going to happen upon or to evaluate the network when we deploy multiple gateways. Moving on to the next tool that we will use to enhance the overall network performance in order to accommodate the massive explosion of the number of IoT connected devices that we spoke about, we will use the machine learning tool, okay? And what is machine learning? Simply, it's making your device smarter by making it learn from its own experience. And this will happen through the use of algorithms which use computational methods to learn information directly from datasets. And as the available data grows, the algorithms improve their accuracy and performance. Now, how do we benefit from machine learning? First of all, automation, because no longer the devices will be reliant on human interaction. And this will improve the overall network performance, okay? Because the rules will always change depending on the current situation, okay? It goes smarter and smarter as more data are taken in, okay? So now there are three primary techniques used in machine learning: supervised learning, unsupervised learning, and reinforcement learning. Of course, if you choose one of the topics concerned with machine learning, you will dig deeper into this. But let's review quickly one of the popular machine learning techniques, which is the supervised learning. It trains a model to predict the future output based on existing input and output data. Okay, so in normal programming, what you do is that you have inputs and outputs, and you get inputs, I'm sorry, and rules, and consequently get the outputs. But with the machine learning, this is not what you want to do. You actually want to have your inputs and you take your outputs in to create new rules to be used again. Okay, so this is similar to using flashcards as a teaching method. The first pairs of input and outputs are introduced to an algorithm. Over time, the algorithm learns the nature of the input-output relationship to predict an output from a new input. Now, one real-life example for this, in order to you to understand what we're speaking about, is that your email spam filter. It learns what spam looks like. This is your input. So the more spam you take in, the more you are able to decide how to separate spam from other email, and this will be your output, the email. Okay, so now we can pin another two bachelor projects that uses machine learning to enhance network performance, and precisely here we're speaking about the LoRa LPWAN, which is the network of interest to support the IoT applications. So from what we just discussed, it is clear that there are multiple configurable parameters adjusted at each end device, like the channel frequency, spreading factor, coding rate, transmission power, bandwidth. And if they are adjusted all together adequately, this can help enhance the network performance. And this will increase the network capacity, which is the number of supported devices on the network. So this means more sensors will be supported by single gateway, or more IoT actuators will be accommodated in a single cell. Okay, this is what we want. And although machine learning is considered a mature field in science, however, few work have applied this in LoRa to adjust these parameters effectively. So the aim of this project is to develop a couple of algorithms to adjust some of the parameters of the LoRa modulation that we just mentioned, and these algorithms shall be developed at the IP backhaul at the network server or the network or the application servers in order to quickly and dynamically give feedback to the gateway, which will be conveyed at the end devices. And so this will help again enhance the overall network performance, which is the primary target of what we are doing for all these bachelor projects I'm offering. Moving on to the paradigm that has gained increasing attraction in the IoT research community, software-defined network. What is SDN? It's not a technology, but an architecture that changes how networks are designed, managed, and operated. Thus, it allows the network to be provisioned as a single entity, and it removes all the detailed knowledge of its topology or components. Now, let's look at the supporting figure here to understand more about that. Looking at the traditional network architecture, you can see that forwarding the actual data and controlling the data are functionalities of each component, each networking component. Okay, so if we have an architecture of 3 planes, data, control, and application, you can see that each networking device has part forwarding the actual data traffic of the user and part controlling how this traffic should be forwarding, and then these components connect to the application plane. And this is what we call the distributed control plane. On the other hand, the SDN architecture simply separates the data plane from the control plane. We call the control plane the brain of the network, or this is the SDN controller here, okay? Because all of the complex functionality of controlling how the network should be managed are centralized at the SDN controller, which in turn connect to the application plane. So, as a simple example, if the components here in the SDN architectures are routers, for example, we'd remove all the routing functionalities from the routers and all its complexity of building routing table and stuff to the SDN controller. Okay, and these control the network and its complexity all are pushed to the edge of the network. So basically, these components here will be data plane components merely acting as forwarding components, no brain. Now, how does this help improve the network or help improve the network performance? First of all, it simplified the network by letting you manage only one or a few control planes, because of course there will not be one SDN controller at the edge. We'll be providing more SDN controls at the edge of the network. And it's going to make it simpler to optimize the application. So when you want to optimize a certain application, you do it once and you push it to the network controller, and it conveys this to all the data plane units involved in the actual data traffic transferring. And this supports dynamic movement, replication, and allocation of vital resources. If you want to change one place to another, you don't have to actually redo this for all the components in the network. You only have to do it at the edge of the network once, and this is conveyed automatically or dynamically to all components out there. So this eases the administrative burden on configuring and provisioning of the network, such as if you want to deploy a certain quality of service or a certain security metric and so on. And this, of course, reduces the complexity. Moreover, or the most important part, it has taken the opportunity to present an API constant across the industry. So if you want to create an application to be written in whatever the language is, you will only configure the network on the fly, because whatever the language you'll be placing in or on your SDN, there has been a standard to convey this information to the hardware components of the data plane and make them shift in real time their service. Okay, so now let's see how SDN can be integrated with the long-range technology of LPWAN, which is another topic that can be pinned here. Okay, the aim of this project is simulation and evaluation of network performance when replacing the traditional core network of the IP backhaul of LoRa LPWAN with the introduced SDN architecture. So yes, the traditional network has been replaced with the SDN architecture, which adds more components at this part. But however, this simplifies the deployment of network functions, which means it will give or provide dynamic reaction to the observed network condition happening at the actual LoRa cell. Okay, and this consequently or intuitively, this will enhance network performance, right? So this is an intuitive conclusion to integrating these two technologies together, or this architecture with this technology. And I would like to draw your attention that this is a new era being explored in literature. So any finding you will come across while evaluating this such kind of integration will be a contribution to science. What does that mean? Easily publishing a scientific paper, for example, an IEEE paper, okay? This really good, looks good in your CV. Reaching to one important and crucial domain in nowadays network, which is securing IoT. As more devices get interconnected, securing them all will be the biggest challenge because you have hardware, software, and connectivity, which all need to be secured for IoT objects to work effectively. Without them, objects can be hacked, and this can result in a wide range of damages from just inconvenience to total blockage. Okay, so to avoid being hacked, security is achieved by three terms: confidentiality, integrity, and availability. These are the three pillars of security. Confidentiality is limiting your data access, integrity, ensuring your data is accurate, and availability is making sure it's accessible to those who need it. So when I want to access my email, I need to make sure it's available there and I have access to it. Okay. Now, one thing I need to mention here to resolve some ambiguity in the use security terminologies, which is that security can actually be classified in different engineers, but it also comes in three different levels. Okay, we have the network security, and this is the kind of security that we deal with in every day because it refers to the measures taken by the network administrator to secure their computer network. And the simplest example of network security solution is to have some sort of password protection. Okay, um, and then we have cybersecurity, to which network security is subset from it, and the cybersecurity is a subset from what's known as information security. Information and subset security are usually or often used interchangeably. So what's the difference? The crucial difference between both is that cybersecurity is concerned with the securing the transferred data regardless of the information this data holds. So what's the difference between data and information? Let's take an example. You have two entities trying to send some data and trying to secure them, okay? Trying to avoid any hackers in between. Among the streams sent in this data, there is this series of numbers, okay? So this is the data that's being sent. But so if I'm working on the data as chunk of transferred bits, for example, this is cybersecurity. But if you'll be checking what this data means, the information this holds, this is my birthday date, for example. So you're reaching now to evaluating the data here, and this is information security, okay? You are stepping into the meaning of what's being transferred, okay? Now, here's a list of some of the security hacks, some of them just present in the IoT network attacks. And we have some of the security attacks that are threat to confidentiality, like snooping and eavesdropping. These are some of the knowns. There are much, much more security attacks out there. And we have some security attacks that are threat to integrity, like, for example, the man in the middle attack. We have someone or nodes that come in the middle of it's like an agent gadget among network nodes to interrupt data communication and operate on it without knowing any communication part, okay? And then we have this engineer that is a threat to availability, like, for example, denial of service. This is total blockage. I will deny the service to a certain application or to a certain server, for example, okay? So in this regard, there are two projects in the security domain that I would like to offer that we shall discuss now, which are one project related to SDN. And as we explained, the control plane is separated from the data plane. So this constitutes that the actual traffic is going in one place and the control traffic is going in other links. So more links are there, and with more components and more links, there are added security threats introduced. Like, for example, we can have a man in the middle attack here between the two SDN controllers, and this is not something present in the traditional networks, okay? This is something new. So the aim of the project is to investigate the possible security attacks in the new SDN architecture, model and simulate one or more of those attacks in an attempt to find a solution for their mitigation, okay? The second topic we have here under the umbrella of security is inspecting the security measures in LoRa LP1. And LoRaWAN is by design very secure it has a mandatory authentication and encryption technique, okay? So in the standard, the LoRaWAN uses the well-known Advanced Encryption Standard, AES. It does some sort of encryption and decryption while transferring and while sending and transmitting the data, okay? It actually has two integrated types for the security of the communication. For each LoRa end device, it generates a network key to be encrypted, and then it is decrypted at the network server. So this makes sure your information is accurate. Okay, this is information integrity. And there is another application key or another security measure by encrypting again the data one more time with an AES, an advanced encryption standard, from the device to the application server. And this conveys what? Data confidentiality, because it limits the data access to only the target application because it's decrypted at the application layer. Okay, application server, I'm sorry. So the aim of this project is to exploit the LoRaWAN security protocol and try to find what are the vulnerabilities there, and if possible, if we can find countermeasures to stop these security challenges. Finally, this is the last topic I have to offer, and it is of special interest to me, vehicle to everything communication, V2X, and it is regarded as a key component in future vehicular networks and intelligent transportation systems. And you can think of this again as part of the evolutionary IoT because, again, cars are speaking to something. And what are the use cases of this kind of communication? We have vehicle to infrastructure, and where you can see traffic lights alerting vehicles to adjust their speed limits, or maybe speed limits alerts, okay? And then we have the vehicle to pedestrians, where you have safety warning to people walking in the street or people riding a bicycle. And then we have the part I'm interested in, which is the V to V, the vehicle to vehicle, where you have warning issued, right? We have warning issued between vehicles to prevent collisions, for example, or traffic hazards alerts shared between vehicles, alerts for emergency vehicles approaching, right? Just to name a few. Now, we can see that the vehicle to everything features are promising in terms of improving traffic safety, degrading accident rates, and offering a new level of comfort for driving. So the aim of this project is to model and simulate vehicle-to-vehicle communication, possibly using the Vine simulator, which is one new simulator that's out there. Now, here's a list of the project that we just discussed. I'm offering 7 projects. Some of them can be grouped together under 1 or 2 themes. And the machine learning projects are co-supervised with Dr. Mehdi Mashali, and the V2V project is co-supervised with Dr. Inji Ali. These are the experts in those domains. Where also you can find here in this in the displayed slide here, you can find keywords covering each topic of your interest, and you can use these keywords to help you research more into the theme you want to work with in your bachelor. One last thing in displaying those clusters is that it also shows your team members, because students in the same cluster will be working together to encourage each other at the beginning of their bachelor project and to help them quickly jumpstart into the details of each individual project. And for a detailed description of each project, please download the document from the link provided in this slide, which will be available in a couple of days, where you will find a brief description describing the project, its major tasks, and a starting reference paper to start with. Of course, there is this famous question of what is the tool used in each project. And let me tell you, these are all software-based projects using C++, Omnet, Python, or MATLAB. But anyhow, I don't want you to worry about the tool used, because as you can see, I have a very detailed timeline with some predefined milestones that I always let the bachelor project students I'm supervising follow. And within this timeline, there are 2 weeks totally dedicated to learning the tool or getting a good grip of the tool you'll be using in your project. So whatever the tool is, I don't want you to worry about it because you will master it. Anyhow, our bachelor timeline starts with the official date on the 26th of Feb this semester. We have the first week dedicated for the background and literature review, so you have a good understanding of what exactly you will do in your bachelor project tasks, which will make you able to submit a project plan. I would like to highlight that we have 2 report submission throughout the semesters before the submission of the final thesis. This makes it really extremely easy to write your thesis, because at the end of the semester you won't be writing from scratch. You have something to write from, okay? Also, you will be using the trendy overleaf to write the thesis and the reports, okay? I think this is an interesting slide for you that holds some important dates. Maybe you want to check that later. I know you guys like these kind of deadlines. Okay, so by this we reach the end of this video presentation. And one last tip I'd like to tell you about your bachelor project is that um, projects or bachelor projects plays a very important role in your career. So pick a project you are interested in, work hard this semester in order to have something that you'll be very proud to show your case in your CV, you know? So get ready for the most energetic days of your GUC life. And this is a memory that will last in you for a lifetime, okay? Of course, if you have any questions, you know where to find me in my office or just send an email. I'm usually very responsive to emails. So good luck and see you on campus soon. Stay safe. Bye.